Hi everyone, this is Teacher Joseph from Brainstem Academy, and today we'll be looking at this chemical test table specifically for IGCSE Chemistry Syllabus. All right. Now, this chemical test table is actually provided for students paper 5 and paper 6, right? The experimental papers. So typically for students, what they have to know is about the table and use this table for their paper 5 and paper 6. Now, but the common mistake students make is that since it's provided, students just try not to understand the table. They just straight up like, okay, table is provided. I'm not gonna, do much practice on it. I'm just gonna use table during exam. So here's the biggest mistake that students can make. Because you're not familiar with the table and then you don't understand what's going on, you end up making a lot of mistakes. And furthermore, even some of the answers written here can actually, it's not actually accepted by the exam board. So the best way for us to master this part is to first understand the whole table, all right? At least understand what's going on. Then do the past papers, right? Apply the table to the past papers and then master it. Now, furthermore, why do I recommend students to understand the whole table? Because this table is actually not provided for students paper 1 to paper 4. So you actually still have to know the table, you still have to know the reactions, and then it would not be provided for those papers. That's why you must know the table, you must understand the table from a deeper manner, which allows you to understand what's going on, furthermore, helps you memorize it better. Okay, so I would like to start with just the very basic one, flame test of metal ions. All right, so the concept is very simple. Basically, when you see an ionic compound, all right, you don't know what's actually inside. Right, you don't know, is it like having like magnesium, is it having sodium, etc. So one of the ways for us to know does the ionic compound contain any of these metal ions is to do something called flame test, which is you take a nichrome wire, right? Typically it's cleaned by dipping it into hydrochloric acid and then put it in a Bunsen burner, right? Take a sample and then put it in a Bunsen burner, and a Bunsen burner must be very hot, right? The air hole must be open to allow a roaring hot blue flame, or else the reaction simply won't happen, or it's just too hard to see by using a red flame. Now, so this is quite straightforward. So if you see these colors, if you see red color, that means the ionic compound contains lithium ions. If it's yellow color, then it contains sodium ion, etc. So this one is actually relatively straightforward, right? Relatively straightforward. In fact, two of them can also be seen when you throw sodium into water or potassium into water. You actually see these two colors as well, right? So it's relatively straightforward. So here, all right, it's more like a unique characteristic. Okay, then we talk about gas tests. Now, for gas tests, all right, so also quite straightforward. It's mentioned here and there. You may have done it in your practical. So usually students have no problem understanding gas tests. So it's really simple. Basically, if the gas is present, you will see a positive test. You will see these reactions happening, these observations happen. Otherwise, it will simply give a negative result. There is no change. All right. If it's present, you give a positive change. You will see these things. If it's absent, then you won't see these things. As simple as that. So one by one, for hydrogen gas, basically it's a very flammable gas. All right. It's also somewhat, you can treat it as an explosive to a certain extent. If it's a very, there's a lot of hydrogen gas, then it's actually somewhat explosive. So what's going to happen is that if you take a glowing spleen, all right, you take a spleen, you somewhat like light it up, all right, light it up, okay, light it up. Then it will actually exhibit a pop sound, right? A squeaky pop will be heard. That's up. Now, then for oxygen gas, if you know your theory well, oxygen gas actually supports combustion. So what's going to happen is that if you take a glowing spleen, all right, a spleen is about to extinguish. You place it, all right, you place it into the test tube that contains oxygen. Then you will see that it actually relights it because it supports combustion, right? It makes your fire burn better. Then you also have chlorine gas. Chlorine gas, as you know, is typically used in disinfectants. It can be not disinfectant, more like chlorine, chlorine as a bleach. So what's going to happen is that if you take a what do you call litmus paper, right? Litmus paper, and then it will just be bleached, right? Due to the unique property of chlorine, when there's water. Then we talk about carbon dioxide. Now, carbon dioxide actually reacts with lime water. If you're curious about lime water, it's actually calcium hydroxide. That actually forms calcium carbonate, which is insoluble in water. That's what makes lime water milky. There's that chalkiness they can see if you bubble carbon dioxide through lime water. Now, then for ammonia gas, it is the only alkali gas in the syllabus. There are actually a lot of alkali gases out there, but for IGCSE specification, that's the only alkali gas. So what's going to happen is that if you take a dim red litmus paper and place it near, all right, to the test tube that produces, let's say do a reaction, it produces ammonia, they will just turn blue. Now, lastly, sulfur dioxide. Now, sulfur dioxide actually turns this reagent, acidified potassium manganese 7, from purple to colorless. This reagent is actually an oxidizing agent, right? An oxidizing agent. It's potassium manganese 7, and then it's basically acidified to increase its tendency to oxidize others. Now, this sulfur dioxide basically reacts with acidified potassium manganese 7, and this solution is originally purple, right? Originally purple. And if we actually turn colorless, right, for those who are interested, it's actually turning into colorless manganese ions. So what's happening here is that sulfur dioxide actually donated electron to potassium manganese 7 and turn it into colorless manganese ions. That's why you see that it turns from purple to colorless. Now, that is everything about gas tests, all right, relatively simple, just that a few things feels a little bit new. Now, then you look at sulfur dioxide, right? Here's the thing. Turns out there's a very similar chemical to sulfur dioxide, and that chemical is sulfide ions. Sulfide ions similarly also donate electrons to acidified potassium manganese 7, and then these reagent similarly return from purple to colorless. Okay, so you can think of it as sulfur dioxide, sulfide. These two are somewhat related to each other. Okay. Then let's talk about some other reactions, but then I would like to just do it like not in sequence, but more like what's connected to each other. So if you have learned your acid-base chapter, all right, you might have learned that carbonate is actually a base, and then ammonium, all right, not ammonia. Ammonia is an alkali. Ammonium is actually an acid. So what happens is, if you take ammonium, right, being an acid, it will actually capable to react with just sodium hydroxide being an alkali. This alkali actually provides hydroxide ions, right? Then it actually forms ammonia gas upon heating, all right? So there are 3 points here. Number one, you must add sodium hydroxide, which reacts with this acid, and then that will liberate ammonia upon heating. So you heat it, then ammonia is produced. Okay, word of caution, for your paper 5 and paper 6, you cannot just say that ammonia is produced, right? Unless they ask you like, what is the identity of the gas produced? Then yes, you can say ammonia gas is produced. But then when it's about observation, observations are meant to be something, observable. You can't really say this. You have to say it instead, refer back to ammonia gas test. You should say that the gas liberated, right, or you can say the bubbles, when you channel the gas through this dim red litmus paper, you will see that it turns blue. Now, similarly, you have carbonate. Carbonate is a base. When this carbonate reacts with acids, right, actually pretty similar to this reaction, if we actually liberate carbon dioxide gas plus water. So, to test for carbonate, you add acid, and then there will be efflorescence being produced. Actually, similarly, this reaction will also produce efflorescence. And then you will actually see that carbon dioxide is produced. Right? You can't see it, but carbon dioxide is produced. Then you cannot say that you see carbon dioxide gas. You have to specifically say that will turn lime water milky. So that's why you can't just use the table. You can't just blindly follow the table. You have to judge the question. You have to understand the question in a detailed manner. All right. My advice is that you understand the table, then you do a lot of past papers, look at the mark schemes, and try to understand how the exam questions are answered. Now, so you can see here, theoretically speaking, basically carbonate being a weak base, you add acid, then it will create, right? It will just liberate carbon dioxide, a weak acid. Then similarly, ammonium being a weak acid, you add a strong alkali that will liberate a weak alkali gas. So it's like, you can think of these reagents are like liberators per se. Liberators, they will liberate the chemical, right? Cause them to produce gases. Right? So these two are somewhat connected, but they are actually under your acid-base chapter. Okay, then let's talk about nitrate test. Now, nitrate test, right, is not exactly acid-base reaction per se. However, they are very similar. It's actually pretty similar to your ammonium test. Just pay close attention. Nitrate, right? Nitrate actually reacts similarly to sodium hydroxide, to heating, and that also liberates ammonia, which can turn damp red litmus paper blue. However, just one key word here that is different: aluminium foil. Aluminium foil. So this is actually a redox reaction. You don't have to know the details, but know that it's actually a redox reaction leading to the formation of ammonia. So you can somewhat link these two together, such that nitrate, just remember that, okay, there's actually extra aluminium, being added to create the ammonia gas. Right. Now, then here comes the terrifying part to most students, right? To most students. Okay. So the rest, right, are pretty much all precipitation reactions. Okay, what's a precipitation reaction? A precipitation reaction refers to usually when two solutions mix together, right? When two solutions mix together, then right, we see that it forms a solid, right? Solid in the solution. Now, this is seen as as a suspension, as a very milkiness, the cloudiness being formed, right? However, these words typically is not accepted in the exam. They want you to write the word precipitate if it's really a precipitate. Okay, precipitates are formed. Now, how does it actually work, right? It depends on solubility. So you have to refer back to your solubility chart that can be found in your salt chapter. Usually your textbooks, they will put it there, right? Solubility chart, like, spam salts. Spam salts are always soluble. And then, sulfates are usually soluble. Chloride, bromide, iodide are usually soluble. That kind of stuff. And then you have to focus on the exceptions. So here, let's talk about these three reactions. Chloride, bromide, iodide are all, right, halide ions. Now, these three halide ions react specifically, right, with silver. Because here's how it works. Silver are mostly soluble, right? It depends. Usually when it mix with others, usually it's soluble. Of course, there are quite a number of exceptions. But then in IG syllabus, you should assume that silver salts are typically soluble, right? Now, here's the special thing. Silver reacts specifically with halides, right? Most halides, chlorides, bromides, iodides, to form an insoluble precipitate. So here's silver chloride being formed. Here's silver bromide being formed. Here's silver iodide being formed. And then they all look differently. So this one, silver chloride is a white precipitate. Silver bromide is a yellow cream precipitate. And then for silver iodide is a yellow precipitate. All right. Now, similarly, sulfates usually are soluble, right? Sulfates usually soluble. Then the special reaction happens when it mixes with barium, because actually, if you know your solubility chart well, right? Let's focus on IG specification. You know that barium chloride is actually soluble, right? And barium nitrate is soluble. So you should assume that barium, most of the cases, the salts that they form are soluble. However, this changes when it reacts with sulfate. So barium sulfate, an insoluble white precipitate is formed. Right? So know that these are, I will usually call it in the class, like I call it special couples. Right? It's like these two fall in love with each other, then they form this special couple. Okay, honestly, how to remember better? Honestly, it's more like practice a lot, and then until it just gets into your head that okay, these things are actually insoluble. Now, then the next thing that we need to cover, right? Okay, so we have mentioned a keyword. So halides, we use silver, aqueous silver. In fact, let me use maybe a different color highlighter. Chloride, bromide, iodide, you use aqueous silver. Right? Then for your sulfate, we use our aqueous barium. Okay, then some students will begin to ask, then teacher, why do we need to add this nitric acid, right? Why do we use nitrate? So here are two things that you must know. Actually, it's within the syllabus. That is, first of all, nitrates are always soluble. Nitrates. Okay, so barium nitrate is soluble, silver nitrate is soluble. Furthermore, it's quite stable. Nitrates are commonly, known as a very stable ion, so it doesn't affect with our reactions per se. So that's why it's favored, right? It's basically very soluble, and then it won't affect your precipitation formation. Now, what about the acid? Okay, so here's the thing. You have to know your solubility chart. If you look back at your solubility chart, you know that hydroxides and carbonates, right, are mostly insoluble, right? Mostly insoluble. So if you don't add the acid, right, potentially this silver or this barium will just react with your hydroxide and carbonate, giving you a false result. It's like it's going to form a precipitate, but it's not actually due to sulfate. That's why we add acid, right? And also you see it's nitric acid. Nitrates are always soluble. This acid is to remove ions like this. So you know that hydrogen hydroxide, they form water, and then hydrogen also reacts with carbonate. That's why specifically they say you need to acidify first, then you add the nitrate salts. Then the reaction happens, it forms the precipitate that you want. Okay? And then same thing here, if they are absent, you will just simply not see a result. No observation, no change can be seen. Now, once you get the hang of these precipitation reactions, right, honestly, the rest becomes quite simple. So here are the common cation ions in IG syllabus, and then same thing, the same concern is that I give you an ionic compound, I don't know what's inside, I'm going to add these two to see which one is present. So here's how it works, all right? If you know your syllabus well, sodium hydroxide and ammonia are both alkali solutions. Alkali solutions actually produces hydroxide ions in water. And what did I say earlier? Hydroxides typically are insoluble. So most of the cases, they are capable of reacting with your metal cations to form insoluble metal hydroxide. So it's like a special couple again. So all of these precipitates like here, right, all of them, right, are actually metal hydroxides. So once you get the idea, right, the first one, the white precipitate form is aluminium hydroxide. Then followed by, of course, ammonium is an exception. That is more like an acid-base reaction. But the rest are all precipitation reactions. This is calcium hydroxide being formed. This is chromium 3 hydroxide being formed. And this is our copper 2 hydroxide being formed. This is our iron 2 hydroxide being formed. And then iron 3 hydroxide. And then zinc hydroxide. All right. So you should know that these reactions are somewhat similar to the previous halide and sulfate tests. Okay, then let's talk about the next part. Now, what about the rest, the details here? Okay, let's just explore it further. You notice that 3 of them are what? Aluminium hydroxide. Then you also have zinc hydroxide, as well as calcium hydroxide. Right? However, your chromium 3 hydroxide is green. Your iron 2 hydroxide is also green. Your copper 2 hydroxide is blue. And then your iron 3 hydroxide is red brown. So why? You have to remember your color of ionic compounds. Color of ionic compounds can be subdivided to 2 types. So one is that if it doesn't contain a transition element, like transition metal ion, that means most likely it is white when solid or colorless when in solution. But if it does contain a transition element, then it will be colored most likely, right? There are exceptions for the rule, but IG syllabus, usually there are not many exceptions. That's why chromium 3 hydroxide is green, copper 2 hydroxide is blue, iron 2 hydroxide is green, iron 3 hydroxide is brown. So then here are some more details. What about how to differentiate chromium 3 and iron 2? Here's the thing. You see that here it specifically says that it turns brown near the surface on standing upon adding these solutions in excess. Okay, so here's how it works. Now, iron 2, all right, iron 2 hydroxide, as it's exposed to air, if you remember your redox chapter, iron 2 can get oxidized to iron 3. The brown substance here is actually iron 3 hydroxide. That's why it turns brown. So that's how you differentiate between chromium 3 hydroxide and also iron 3 hydroxide. Now, what about the rest? Soluble in excess, insoluble in excess. Okay, here's my honest opinion. As for IG, right, IGCSE syllabus, this is not commonly tested in other papers. So my advice is that if you aim for a higher score, you aim for somewhat perfection, maximizing your marks, then yes, maybe you have to know this. Otherwise, I think it's better to do it 50-50. Soluble in excess, insoluble in excess. Let's be real, all right? It's like the syllabus is so long, you can't remember every single thing. All right, so somewhat, I would say, somewhat like a 50-50 chance. So if you couldn't remember, then at least fill something in your test paper. Okay, but then if you really want to know the reason, okay, if you really want to know, here's how it works. For soluble in excess, right, typically it works in two ways. Either they are like aluminum hydroxide. Okay, let's focus on sodium hydroxide first. Like here, right, aluminum hydroxide and zinc hydroxide. If you remember, Z oxides are amphoteric oxides. So it turns out your zinc oxide, zinc hydroxide, and aluminum hydroxide are amphoteric. And what do amphoteric oxides, amphoteric hydroxides, like, what do they do? They actually react with alkali. That's why they're soluble in excess, but not for your calcium, right? Not for your calcium. Okay, what about the rest? The second theory is not in IG syllabus, but if you're interested, you can search it up. It's something called formation of complex ions. Formation of complex ions. Okay, search it up. Basically, this one is more towards A levels already, where they react, right, to form soluble complexes. That's a potential possibility. And honestly, it's kind of random, right? It's kind of random. So my honest advice, right, is that at least your fundamental is everything that we covered so far. Once you understand it once or twice, and then then try to apply it, then you actually have a smoother journey in your papers. All right, and that's pretty much it for this exploration of the whole chemical test table. So if you're struggling in IGCSE chemistry, you need help for IGCSE chemistry, right? I'll be willing to help you. You just have to click the link in our, below our, maybe our website, our social media page, right? You can see our link, you can fill in your information, and then let us know how we can help you. We provide IGCSE chemistry tutoring, all right, to help you specifically to prepare for IGCSE chemistry exam. All right, we have modules, we have notes, we have everything. So it's just that whether you want to accept our help or not. All right, so anyway, good luck to your exams, and I'll see you in the next one.